Hello, AP Calculus BC students. Mr. Record here. We're going to do our final example in our power series presentation. Up until this point, we've done quite a few things with power series by writing them as representations of some other functions. In a previous example, we actually found the power series for arctangent of x, and it actually ended up producing this little guy right here. So you can always kind of tune in and watch some of the other videos that I've presented to kind of get brought up to speed. But in this particular video, what we're going to be doing is going back and looking at the accuracy of this particular power series and see exactly how well it's represented. So in order to do that, we read through the problem. We're going to use the power series f of x as arctangent of x, represented by this thing. And we're going to approximate the arctangent of 1/3. And we're going to use the fact that our nth r term is less than or equal to 0.001. So to get the ball rolling, we'll say that the arctangent of 1/3 would be equivalent to this power series, where the x changes to 1/3, of course. Now, what's very important to note in this particular problem, more than anything, is the fact that this term here resides within our series, within our summand. And that would alert us to the fact that this is indeed a alternating, almost wrote the wrong word there, this is an alternating series. And when it comes to finding errors with alternating series, we've been taught, or hopefully we've been taught, that that first neglected term is going to end up being your particular error in this case, or sometimes we call it the remainder. And that's the role of this particular guy here. This 1/1000th is going to serve as that particular error. So to find this, the best way is just to start listing out your terms. So we're going to begin with n being 0, and of course -1 to the 0 is going to be 1, and then by the time we raise 1/3 to the first power and divide by 1, our first term is going to be 1/3. I doubt that we're in jeopardy of being able to stop the problem at this point and say that that would be our approximation, because we're pretty far away from having a term that's going to have a value that's less than 1/1000. So we're going to continue this. And it's going to be 1, so that's going to give us a negative sign. 1/3 to the third power. I'll tell you what, let's take it easy and we'll go ahead and list all of this out. 1/3 to the third over 3. Now, what I'm going to do is begin to simplify this in this next row. So 1/3 is raised to the third power is going to be 1/27. And when that's divided by 3 again, we're going to have 1/81. So it seems like we're still pretty much in the clear, and we've got a ways to go before we're going to get a 1/1000th value, or less than a 1/1000th value. So we're going to move on. We're going to let n be 2. That's going to give us a positive. And then 1/3 is going to be raised to the 5th power. 2 times 2 plus 1 is 5. So 1/3 to the 5th, I believe that would be, let's see, 3 to the 5th. 3 to the 5th is really 3 to the 4th times 3. And we've already, you probably see that 3 to the 4th is going to be 9 times 9, or 81. So 243 is what 3 to the 5th is. But I'm going to divide that by 5, so I need to do another multiplication here. And I want to show you that you could indeed do these problems without a calculator if it came down to it. That would be 12, right? 243 times 5 is 1,215. So that would be my third term. And then all of a sudden we say, whoa, wait a minute. I noticed that this particular guy here does meet the requirement of being less than 0.001, because remember 0.001 is 1/1000. And seeing how this denominator is larger than 1,000, that makes the entire fraction smaller than 1,000th. So that means that we really have our requisite terms that are needed in order to find this sum, and that would just be these two guys. Had this been a free response problem, I wouldn't really see any problem if you just stopped right here, because you have a difference of two things that would be numerically equivalent to your answer. However, if this were by some chance a multiple choice, and it would make a good multiple choice problem, to be honest, you would probably want to go ahead and combine them. So the 1/3 is just the same as, to get a common denominator of 81, we could call it 27 over 81. And then once we do the subtraction, we get this. And 26 over 81 indeed will be our answer. Now I wanted to show you something graphically. I'm going to switch over to the TI Inspire here. And one thing I wanted to show is if we were to use a calculator to figure out what the arctangent, inverse tangent of 1/3 is, to 6 places we would get 0.321751. And comparing that with 1/3 minus 1 over 81, we get something that's sort of in the ballpark. And in fact, if we were to say subtract the two from each other here just really quickly, we find that our error or our difference here is certainly going to be within that threshold of under 0.001. Now graphically, you've got sort of an unusual sketch here. Let's see if I can find it. This particular graph is sort of kind of precarious to render. I know that if you're one of my students, we've talked about this many times, that you're really going to set yourself up for a lot of disappointment if you try to let that upper bound truly be infinity, because you just won't have enough calculating power most likely to figure that out. So usually what's safe for the TI Inspire handheld is to go to 100. If you're using the computer software, you can probably go a little higher, but it really doesn't matter, because using 100 I think is going to kind of reveal what I need to reveal, and that this power series has a portion of it that seems to be very kind of disciplined and sort of behaving well. So if we were to perhaps go in and actually sketch the inverse tangent of x, we'll find out that he will lie very nicely along that nicely behaved portion of our power series. And since 1/3, which is right around in this region here where I'm pointing, lies within that interval of convergence, then we have a very reliable means by which to approximate. When you start moving outside that interval of convergence, then certainly all bets are going to be off. So hopefully this takes care of that particular example 5 in our notes. They're very common, and if they look a lot like some of the things that you've worked with back in your alternating series studies, then you're thinking the right thing, because it really is the exact same thing, only applied to now a power series. So I hope this video helps you out, and we'll see you next time.